Okay. Yeah. If you haven't had a chance to look at the other video, please watch it. That way, you know the beginnings of this. But the next lab really talks about the factors that influence the rate of the reaction. So this is chapter 14. I'm not going to go over everything I discussed, but what I'm going to go over is the order of reaction. So remember, this chapter talks about the rate of the reaction. So when I was learning this in school, I used to be an athlete. I used to run. I ran track and cross country. So when I got to this chapter, I was trying to bring my world into chemistry. So I was thinking, like a coach, what does the coach do to prepare us or to influence our ability to run faster, right? Different things. And the coach has to think in a way as an engineer. What can he do to make us run faster? If you're running a relay race, what can he do to make sure the whole group wins, right? In a relay race, you have four athletes all competing to make sure that as a group they win, right? As we're going into the order of reaction, the order of reaction talks about each individual, so to say, in the race. How does each player, how does each athlete contribute to the whole? So think about the reaction as being the rate. The reaction as being the race, reaction as being the race, and then the individual as being the reactant. So you want to know there's some people who run fast, there's some people who run slow. In the end, how does each individual influence the race that they're running? Do they make the time shorter, therefore they win, or do they run too slow, therefore slowing the whole group down? And as far as the coach is concerned, when it comes to a relay, the coach has to be very strategic in where he places the runners, right? If you watch relay races, the last person usually has to be the fastest. That last person can sometimes erase the mistakes of the other people by catching up on time. Okay? And then the first person has to be fast, the last person has to be fast, and then the people you have in between can be slower. When it comes to the reaction rate, we'll see how the slowest reaction in the steps can actually influence the rate of the reaction. So the order of the reaction, as we talked about last week, is the number that talks about how each reactant influences the reaction rate. So I worked this out last week just to show you that. Let me start right here. Yeah, we have this rate law. So this is an example of the rate law that I worked out last week. And in the rate law that I worked out last week, the rate law usually has this format where you have the word rate. You always leave the word rate as rate. You don't put a number there. And this is the rate of the reaction that's being monitored. Equal to, you always leave the constant as K. So if they ask you to write a rate law, you will write rate equal K. This has to be written that way. And then here you write, depending on how many formulas affect the rate of the reaction, each formula, each chemical formula that affects the rate of the reaction, and most of the time what you have here are reactant formulas, you will put them in parentheses. So what I worked on last week, this is the answer I got. The rate of the reaction is affected by two chemicals. Well, the way I've written it here. Two chemicals may be able to influence the rate of the reaction. The first one is NO2. The second one is CO. So the question is, how do they influence the rate of the reaction? Well, looking at the superscript here, this is the order of the reaction. The order of the reaction tells you how each formula in the parentheses influences the rate. So since I worked here, let me go ahead and analyze this as we go into the details. So rate is equal to K NO2 raised to the power 2 CO raised to the power 0. So we see that NO2 is second order, right? Second order based on this number here. So if somebody asks you what is the order of reaction, you would say NO2 is second order. But what does that mean? What does this mean? What's the implication? How does knowing that NO2 is second order influence the way you design the experiment. This means when concentration of NO2 is doubled, the rate of reaction is quadrupled. Oh, I can't spell quadruple. Hold on. I think it's just U. Yeah, these phonetics in English, man, it's like a whole different thing. So you can kind of isolate, right? Because we're trying to see the influence of NO2 on the rate. So to isolate it, I'm just going to write rate equal. K is a constant, so you can write it in or you can leave it out because K value is not changing. So for this purpose here, I'm just going to leave K out. I'm trying to see what kind of influence does NO2 have on rate. So since we said NO2 is second order, okay, that means if you double the number in here, you have to square it, right? That will double the rate. That's what second order means. So to know a second order is good, but you also have to know the implication. What does this mean? How does this play out, right? So let me show you how doubling NO2 will change the rate. Say NO2 has a concentration of, let me pick an easy number, 2 molar. If it's 2 molar, I'm going to figure out the rate. Rate will be equal to 2, the concentration, and then square it. So rate will be equal to 4, right? And then let me go ahead and double the amount of NO2. If I make NO2 now 4 molar, I can now figure out the new rate because the relationship between NO2 and the rate is consistent. NO2 always influences the rate in a second order way, okay? So now I can figure out the new rate of reaction when NO2 is doubled. 4 squared, what is this? 16. So the rate when NO2 was 2 is 4. The rate when NO2 was doubled is 16. How is the rate changed? From the original rate 1 to rate 2, you can see right here, times 4, times 4. That's what I use the word quadrupled, right? It's quadrupled because of the order. So we're going to go through line by line and look at how zero order influences the reaction, first order influences the reaction rate, and then second order. We have already seen second order, right, based on this question. Then I mentioned here again last week that what about CO? CO is raised to the power 0. What does that mean? So CO here, the chemical CO, carbon monoxide, is actually zero order. Sometimes they call it zero order. Some book call it zeroth order. I don't know what's up with that, but hey, this is the terminology they use, zeroth order. So I'm like, okay, zeroth order. What does zero order mean? In maths, any number x power 0 is equal to 1, right? So we're going back to the math rules. So rate is equal to the constant times CO power 0. Okay. Once again, we're trying to see, based on what I did last week, what this means. So rate is equal to K times CO power 0. This just means that since CO power 0 is the same thing as 1, I can rewrite this as rate equal to K, and then this whole thing becomes 1 times 1. So rate is constant, okay? So this just means no matter what I do to CO, the rate is going to be the same number. It will not change. So changing concentration of CO will not change the reactant. Okay, so remember how I started this whole lesson today with that whole track analogy, right? Especially the relay race analogy. Since people know the mechanism of running a relay race, they tend to give the middle positions to the questionable runners, the one that you can't really trust because they're not consistent. They can be slow sometimes, fast sometimes. Kind of, to me, as you view them like the zero order people, you put them in the middle, right? Because the first and the last runner can kind of overcome their errors, right? Bottom line here, we know that a zero order chemical will not influence the rate of the reaction. So if your boss tells you make the reaction go fast, don't even try to change this amount here. You're just going to be wasting chemicals. It will not make the reaction go fast because you know ahead of time it's a zero order. Okay. So we're going to work another problem out. I wrote it to myself, start here. So here we have a balanced equation, and we're being told reaction. Normally, I don't do the for practice, but I didn't want to start this lesson going over the new stuff, so I wanted to do this again. We're told here, consider the following equation. So we have a balanced equation. Initial rate, we're going to be figuring out the reaction order, okay? The initial rate of the reaction is measured at several different concentrations of the reactants with the following results. So we have this balanced equation, right? Remember I mentioned last week, I'm going to keep referring to last week. That way, if you got a chance to skim over the PowerPoints, but you didn't really get stuff, I'm still referring to it, okay? So at this point, somewhere in the PowerPoint, I told you that we're trying to figure out the rate of the reaction, how fast the reaction is going by only studying the reactants. When we started last week, we're studying both the reactants and the product. But from here on, we're only studying the reactants. So we're looking at the rate of the reaction from the reactants. And we're asking, how are the reactants making this reaction go fast? So anything that's a reactant here can qualify in our rate law, okay? So the general form is rate is equal to K times whatever reactants you have in brackets. So even though I haven't done my math yet, I can write a mock rate law. Okay, so I'm going to write it here. I know in the end, my rate law will look something like this. Rate equal K, and then I have two chemical reactants. The first one is bracket CHCl3 raised to the power M. Second formula, Cl2 raised to the power N. This is my generic rate law. Okay, I haven't done the work though. I'm going to be doing the work like it says here. Find the reaction order. I'm going to do the work to figure out what M is and figure out what N is. Once I figure those out and I plug them back into this equation right here, then I get my real rate law. So this is kind of like a placeholder. It's like a placeholder equation, right? Rate law until I get the real one. Just to let me know ahead of time, this is what my goal is, okay? You're figuring out the reaction order, meaning you're going to try to solve for M. So solve for M and N in the rate law. Once I solve for M and N, I'm going to replace M and N in my holder rate law, and then I have gotten my rate law, okay? To solve for the order of reaction M and N, you're always provided with a data table because you only get it from experiments. So it says here, the initial rate of the reaction, this is the rate right here, is measured at several different concentrations, aka an experiment of reactants with the following results. Okay, so I have the one reactant concentrations in molar, the second reactant concentrations right here. Okay, so we're going to do the work required to get the order M and N. Okay, so telling you here, finally the question. From the data, determine the rate law. Now I already wrote my mock rate law right here. I can just be lazy and copy it over. I mean, oh, they have updated this app. Okay, there, copied it over. This is not my answer, right? I still have to replace what M is, and I have to replace what N is. to get my actual rate law. And then I'll figure out the rate constant. Then I'll solve for K. So here I'll be solving for K. Okay, I can do this. So how do I get M and N? Let me go ahead and add pages here. Okay, so I need my table here to get these numbers. And I'm going to show you what colors I choose, or I'm going to color my choices. Let me put this right here. So I actually need to solve for M. I'm going to write my rate law. Let me move this rate law down here because I actually need this for visual purposes. I like to write my rate law ahead of time because it visually helps me to see what I'm looking for, and it does help me to focus also. So right here, I'm going to start by solving for M. When I was a student, I wasn't organized because I was still trying to figure things out. So sometimes I'll just do stuff and I'm like, what are they solving for? I don't know, one of them, whatever. Okay, I'm going to be more structured because now I'm a teacher. Okay, solving for M. So if our goal is to solve for M, that means that we're trying to solve for M. So in our calculations, M should remain. So to solve for M, my strategy here is to pick two experiments where Cl2. Why am I picking Cl2? Because Cl2 doesn't have M on it. Cl2 is power N. So where the Cl2 concentration is constant. Okay, so pick two experiments where Cl2 concentration is constant, because I'm trying to make sure when I cancel things out, M remains. So to solve for M, I'm writing here on a side note, make sure M remains. Let me tell you what I did, okay, as a student. Sometimes my plan was to solve for M, but I'll cancel out M. Then just go back and change your title and say solve for N, okay? So pick two experiments where Cl2 concentration is constant. So I'm going to Cl2 right here. I gotta pick two experiments where the number in Cl2 is the same. Oh, I can't erase that. So what do y'all think? Let me label these. Experiment 1, 2, 3, 4. So what experiments do y'all think I should pick where the concentration of Cl2 is the same? So we're looking at this right here. What do y'all think? I have 4 experiments. The experiments are, you're reading them across, right? So I need to pick 2 experiments where the concentration, the number on the concentration. So we have these 4 numbers I'm looking at here, where the numbers in the concentration of Cl2 remain the same. So which one do you think I should pick? You can type in your answer. Anybody? Okay. I'll take the first experiment and the second experiment. The number is literally the same, right? 0.010, 0.010. Okay. Now, when it comes to writing it out, though, the question is, I'm going to be writing the rate law for the 2 experiments, experiment 1 and experiment 2. Do I want to do, and then divide the 2 rate laws? Do I want to write the first one first or the second one first, which is which? I usually look at the remaining numbers, these 2 and these 2. I like to put my bigger number on top since I'm dividing. I don't want to deal with fractions. As a student, I got decimals, fractions, and you need to be able to intuitively see the relationship between decimals or fractions to see the exponential relationship. That's too deep. So if I flip it, it makes my life a lot easier, right? So what I mean by this is once I pick my 2 experiments. So my experiments are experiment 1 and experiment 2. That's my choice, okay? How am I going to do it though? I'm going to write the rate law. So I'll say here, write rate law experiments. I picked those. Second one, write rate law for both experiments. Okay, remember the bigger one will be on top. So essentially I write experiment 2 over experiment 1. Okay, so the rate law looks just like what I had here, right? So maybe I can copy this again. This is being copied a lot. I'll put it right here so I can see. It's just like this, only we're trying to solve for m and n, right? M and n. Okay, so in the place of this word rate here, I have to find the rate for experiment 2. The rate for experiment 2, let me use a yellow highlighter. These are the numbers I'm working with in writing the rate law. My rate for experiment 2 is this number right here, right? And then I have to use the units too. So 0.0069, 0.0069 m over s. Ooh, I wrote too big. Sorry, y'all. I write like I'm on campus and I need a little bit more space in that. 0.0069 big M over S, right? That's the unit, okay? Equal to, and I have to write K. I don't know what K is, so leave K as is. And then open parentheses, and I have to write the concentration that goes with this formula here, CHCl3, right? So let me find CHCl3. I'm doing experiment 2, right? That's this number here, 0.020. I put 0.020 raised to the power m. Well, the unit here is m, raised to the power little m. The next formula, that's right here, the number that goes with Cl2 for experiment 2, that's this number right here, 0.010. 0.010 m raised to the power n. So I did that for experiment 2. I see I wrote a little too small here. I like these to be a little lined up. I know, it's those little obsessive tendencies I have, right? Excuse me, guys. For some reason, it makes me feel better. It has nothing to do with my efficiency. It just makes me feel better. Okay, that's my experiment 2 rate law. Now on the bottom part, I'm going to write my experiment 1 rate law. Okay, experiment 1 rate law, I have 0.0035 0.0035 big M over S equal, again, I don't have K. You never have K. I shouldn't say you never. Never say never. Okay, you normally don't have K in the beginning, right? So K is always written as K is the constant. And open parentheses, then you have to find the number here. So I'm done with this part. I've done K. The number that goes with CHCl3 for experiment 1. So I'm done with these, right? I'm done with that. This number is what I'm writing next, 0.010. 0.010 m raised to the power m. This is the same number as before, 0.010. 0.010 raised to the power m. I mean n. Okay, don't get too hung up on these letters. There's some books that use HK, whatever, PQR. I've seen some XYZs. So the M and the N are the most common ones, but I've seen all kinds of letters out there. Okay. And I'm like, why are we using different letters? Different author, but same meaning, same purpose. So remember, we're trying to solve for M, right? So cancel out what's common. I'm going to cancel out the units, cancel out K. K is the same. It's the same reaction, so K is constant. This whole number and its exponent matches the bottom number. I mean, you picked up the experiments on purpose to cancel out the N part, right? So that cancels out. Now we can consolidate, right? We have 0.0069 here divided by 0.0035 equal 0.020 over 0.010 raised to the power m raised to the power m. Okay, this is what we're left with. Now, mathematically, we're going to consolidate this even further for our own purposes. So on the right, we consolidate the numbers, the base numbers, because the exponents are alike. So it's going to be 0.020 divided by 0.010 raised to the power m. So technically we're consolidating the exponent, not the base, yeah. Because since the exponents are alike, we pretty much rewrite it like that, okay? And then I can go ahead and solve the number on the left. Actually divide it out. Oops, my calculator is off. 0.0069 divided by 0.0035. 1.971. Okay. Then I have this number on the right. So here, when you divide these two, 0.0020 divided by 0.010, I get 2. So here, 1.971, we can round this up to 2, y'all. I don't like to complicate this stuff any further. I round it up to 2. Here we have 2 power m. Mathematically, if the base numbers are equal to each other, then the exponent numbers are equal to each other. So you want to rewrite 2 as a base number raised to an exponent. So I'm going to rewrite this as 2 power 1, which is the same thing as 2. I'm not changing the value of this. And then make this equal to 2 power m. So m is equal to 1. So what was this reactant again? The reactant that we wrote first, CHCl3, the m, m is power 1. So that means CHCl3 is first order, right? Because we got m equal 1. So now we can find the order for the second one. We can now solve for n. So here I'll say to solve for n. To solve for n, like we did before, we're going to pick 2 experiments where this time, let me see, how do I copy this? We're picking 2 experiments. Oh, this is not going to work. I have to actually write it down because it will copy as a picture. Pick 2 experiments this time where CHCl3 is constant. It's not changing. So what do y'all think? Our focus is now on this. We already solved for this. Now we're trying to help this one out, right? This other one out. So which 2 experiments should we pick where the amount in the table of CHCl3 is not changing? Can you tell? Where the amount of CHCl3 is the same? Yeah, that's going to be experiment 2 and experiment 3, right? Again, I look at the other 2 numbers, and 3 is bigger than 2. Okay? I'm going to need this table here. So let me see if I can copy this over. It's harder to go back and forth and back and forth and back and forth. So let me scroll down here and we see. To solve for this, I'm going to put this image down here. Okay. So I'm using these experiments here. Let me highlight them. It's these experiments here. So I'm doing experiment 3 over experiment 2. Experiment 3, as I'm writing the number, I'm going to be highlighting. That's why I erased that. I'm starting with this one here first. Remember, I'm following the order rate equal K CH3 C. I'm messing up the formula. CHCl3 raised to the power m, Cl2 raised to the power n. I'm following that order, right? So my rate has to be this number. I'm starting here. I'm using the bottom number. 0.0098 m over s, starting with that number, equal K. So I did this number. I'm doing this number next. K, leave it as is. Find the concentration of CH3Cl3, which is this number right here. 0.020. And the unit here is M. Now remember, we already solved for this order, right? For CH3Cl, we said M was 1. So I can actually put the 1 here. I already solved for it. Next one, what is the number that goes with Cl2 in experiment 3? 0.02. 0.020 raised to the power n. You can't put an n number because we don't know what n is. We're doing all this work to find n. Okay, so I'm done with these numbers. I'm highlighting them to say I'm done with them, right? Done, done, done. Do the same thing for experiment 2. For experiment 2, I'm starting with this number here. 0.0069 m over s equal k. And then my top number is, oh wait, this number, so I'm done with this. This is done, rate k. Now I have to do CHCl3. CHCl3, that's going to be this number right here. 0.020 m raised to the power 1, right? And then the next one, so I'm done with this number. 0.010 raised to the power n. So I did this number already. I just did this number. I'm done with my experiment part, okay? So cancel out what we have in common. K, cancel out. This, cancel out. Then we're going to bring together what we have left. Units cancel out. So 0.0098 over 0.0069 equal. I'm going to do a quick consolidation here because we know how this is going to go. 0.020 divided by 0.010 raised to the power n. Oh, 0.0098 divided by 0.0069. Ooh, I get 1.42. This is interesting, y'all. 1.42. I may have to do some logarithm stuff. 0.0069. Sorry, 0.0098. Let me make sure this is correct. I've never done this problem before. Yeah. 0.0098 divided by 0.0069. Why they give us a number that looks like that? Trying to force us to use the logarithms. Okay. Then this one here is going to be 2. Right? Divide these two, you get 2 power n. So this is one of those problems where you can't just round up because technically 1.42 is not, this is not 5. So you can't just round up, right? And then it's too far from 0, so you can't just easily round down. So here's where you have to use the logs, right? Man, they caught us. When I say us, it's more like me. So this is the part that I had skipped over last week saying, we don't have to do the logs for the most part. But since we've come to this point here, I'm going to show you the logs and how they did it. Oh, let me go a step back here. So when you get to this point right here, this point here, you take the logs of both sides. So there was a part that's missing here. We had 1.01. Can you imagine doing a log of this? Equal log, 1.01 equal 2 power n. And then they took the logs of both sides, okay, to figure out, and they still had to round up, right? So that's what we're going to do. We are kind of like right here, we'll take the log of both sides to solve for n because I can't just round up. Suddenly the situation we have here is slightly a little bit more complicated than what we saw last week, so I can't just round up. So in this situation here, where was I? Right here. Take log of both sides. That's my strategy. Yeah, let's see. I'll take a log of 1.42 equal log of 2 power n. As far as logarithms rules go, this becomes n times log of 2 equal log of 1.42. Okay? And then to solve for n, divide by log of 2, divide by log of 2, and that gives us what n is. Okay? So I'm going to add one page to it, and that will help us resolve this. Okay, so what is n? N is equal to, what's log of 1.42? Let's see, using my calculator, second log function, 1, my answer. Okay, I'm getting the top number here. It's going to be 0.152. The bottom number, log of, cheap calculator. It's the second function here. Log of 2, I'm getting 0.301. So I'm going to take my top number. I hope it comes into a nice number divided by my bottom number. And I get 0.506. So the way it worked out here, my order for this is 0.5, which is the same thing as half order. A half order is possible, y'all. It is possible. So what we are saying is Cl2 is 1/2 order. So Cl2 is a half order. They should have made this problem a little bit easier. But anyway, this is what I get for this one here. Okay. So looking at that, I'm trying to check to make sure. Okay. So looking at this here, then we'll go ahead and write our rate law. So they want us to write the rate law. Rate law. This is our rate law right here. The first answer. Rate is equal to K, CH, Cl3, and then you write the bracket, raised to the power of 1. Since the 1 is implied, you leave it out. And then you write open parentheses or open bracket, Cl2 raised to the power 1/2. It's not common at you guys' level to find fractional orders, but the fractional order is possible. In our case, no matter how I looked at it, I got a fractional order. Okay, so this right here will be your rate law. That will be the first answer you provide. Rate law, you write it in this form. Okay, the second part, they said solve for K. To solve for K, choose any of the 4 experiments we have, any 4. Okay, so pick from the ones that we have, any of the 4. Let me pick the first one because the first one is a lot easier for me. It's just right there. I want this one here, this first one. So I'm going to copy that so I don't have to try to remember. Okay, this is the first experiment I'm using. I'm going to plug in the numbers in here and then solve for K. So rate equal K, CHCl3 raised to the power 1, Cl2 raised to the power 1/2. Okay, so in the place of the word rate, I'm going to put this number, 0.0035, right? And then K, I don't know what K is. I'm trying to solve for K. For this first formula here, I put that number, 0.010, raised to the power 1. Actually, let me use the units here. I'm being lazy. I have to use the units. M over S, K, 0.010 M, raised to the power 1. The 1 is implied. Cl2, 0.010 raised to the power 1/2. And I'm going to solve for K. So to solve for K, to solve for K, I left the unit out there too. Man, I'm forgetting the units. To solve for K, what I'm going to do here is I'm going to open up these parentheses. Okay, let me work this part out first. 0.01, and then this is raised to the power 1/2. So I'm going to write power hat 1/2. Okay, so like the square root of this ends up being 0.1. Okay, then I write the unit m power 1/2, and I'll deal with that as it comes along. And then right here, I'm going to multiply this by this. So 0.010 times m. This is a weird problem, but yeah, times m. Okay, then we have this k right here, and then we have 0.0035 m over s. So multiply out the numbers, 0.010 times 0.1. So this is times 0.010. I end up with 0.001 here, and then this and this, I kind of get an m. When you multiply m, which is essentially 1 times 1/2, I end up with m 1/2. I'll leave it as is for right now, okay? And that's my unit. And then, of course, times k. And then here I have 0.0035 m over s. This is one of those weird hypotheticals. So divide both sides by this number to get k by itself, 0.001. Divide both sides by 0.001. This cancels out. 1/2, right? This cancels out, and now we have m power 1/2. So we end up with 0.0035 divided by 0.001. I don't know. I should have probably used the worksheet instead of this question. It's very weird, but I end up with 3.5. This ends up canceling with one of those, so I end up with 1. The unit is, the number is 3.5. 1 over m power 1/2 times s. This is what I get for k. Okay, a very weird unit. But don't obsess so much with the unit, because I don't see in most of your homework, the ones I assign, at least, we don't have fractional units like that, because I haven't given you ones that have weird orders. I normally don't do the for practice one, but just because I wanted to give you guys more practice, I did that one. So the plan is always this. In this kind of questions, the steps are usually very similar. You are asked to figure out the rate law. Write yourself that placeholder rate law and include all the reactants in brackets raised to the power of whatever letters you choose. If you choose Mn and there are 3 formulas, you can use MnP. Don't use MnO because O looks like 0. Okay? If there were 3 formulas in your reactant, write rate equal K times the first reactant, second reactant raised to the power M and P. Okay? Solve for M, solve for N, solve for P. To solve for M, once again, pick experiment where the other 2 sets are constant. To solve for N, pick the experiment where the other numbers are constant, and you figure, once you practice this, you figure out which ones to pick, right, to solve for the different exponents or the different orders. Use exponent rules to solve for M. Use exponent rules to solve for N. If you get stuck, like the weird one we had right here, with this being 9a, you end up with log. Yeah, you end up with logs. Hold on a second. 9, 8 divided by 6, 9. Yeah, you end up with logarithms, like the weird one like this. For the most part, though, remember I told you guys, you won't have weird questions like this, right? And so you continue and then you get your answer. Once you get your rate law, after plugging in the value of M and N, only then can you solve for K. To solve for K, pick any one of the experiments provided for you, put the rate number here with the units, and then the concentration here for the experiments that you picked, and then plug in the numbers and solve for K. You want to write K with the units, okay? K in this section has units. So let me continue from here. Now that we've seen all of these, the other thing that you're gonna have to be able to produce is the overall reaction order. So this here is a hypothetical situation to help you answer this question, okay? This is something that you need to know, which is how to provide the overall reaction order. We know the reaction order for each individual reactant, like we know the speed of each athlete in the 4-people race, the relay race, but we want to know what is the collective influence, right? Now that we know each athlete, now how can we look at all 4 athletes and how do they together place in the competition? What is their collective times? Okay, so what is the overall order of the reaction? The overall order of the reaction is very simple. It says here, to get that, sum of the exponents of the reactants is called the overall order of reaction. Just add the exponents, okay, or what we call the order of reaction. In other words, overall order of reaction is just M plus N, etc. So if you have 2 formulas that actually influence two reactions that influence the speed of the reaction, add their orders, and you get the overall order. So they give you an example here. Say the rate law for the following reaction is as follows. So this is a hypothetical scenario. Let's say the rate law is rate equal K times NO, which is actually second order, O2, that is first order, right? Second order, then nothing that's implied here is essentially 1. And they tell you the reaction is second order with respect to NO. So the reaction rate, if you're just looking at how the reaction is influenced by NO, it's going to be second order with respect to NO. How's the reaction rate influenced by O2? The reaction rate is going to be first order with respect to O2. Okay, O2 essentially is first order in the way it influences the rate, but the way you write that is this way. Okay, this is looking at the individual athletes, the individual reactants. But then they ask you though, together, collectively, how do they influence the rate? You add the two. Since it's second order for the first one and first order for the second one, it's going to be third order overall. So as a group, as a duo, this is how they influence the rate of the reaction. Okay, so hopefully that makes sense. This part here is really, once you get the rhythm of it, it's not that tough because they don't do a lot of unpredictable stuff. It's the unpredictables that tend to catch me off guard, but if they're predictable, I'm like, bring it on. Okay, now I've kind of talked over this, so this part will go a little faster as far as the implications is concerned. You want to know generically, so this is kind of going into the whole generalization, because you know chemists like to do this, generalizations. So you want to know in general what a zero order rate law looks like. So like in general, a zero rate law, this is the rate law for a zero order reaction will look like this. Rate is equal to K, and A here stands for the reactant. So A is just some generic reactant. Kind of like in math, X is some generic number you're solving for, what is wanted. So this is the general rate law, right? Rate is equal to K, A raised to the power N. So we're going to be working out getting the zero order. If a reaction is zero order, the rate of the reaction does not change or does not depend on the reactant concentration. That means they're saying here, if you double A, this will have no effect on the reaction rate. That's what I mentioned earlier, right? So the rate law is really rate equal K, A raised to the power 0. You don't leave it as that. You can leave it as that, or you can write rate equal constant. But remember, chemistry is a problem-solving class, right? A problem-solving class, as we try to understand the elements, you want to know things more than one way because you have different people communicating the same information. They can write the zero rate law this way, or they can write the zero rate law this way, where it's implied the A concentration raised to the power 0 has already been factored in. So this is what you have. So you want to know it this way or this way. So if they say there was a reaction where the rate did not change in response to the concentration of the reactant being changed, then you're like, oh, they're talking about a zero order reaction. Okay, then you keep reading. Okay, so for this part here, make sure, I'm going to highlight the places that you need to know. Of course, you want to know this is a zero order reaction, right? Zero order right here. You want to know the generic form, this part here or the bottom part. Then you want to know the implications. So the implications here is what I wrote in this picture here, implication. So to make this part a little simpler, what I did was I calculated the rate of the reaction by changing the concentration. So you can see here, this is supposedly my makeup experiment 1. You want to know how to do this part here, right? Experiment 1, experiment 2. So what are the implications? Like, how do you make the rate either faster, slower, or not change? By changing the concentration of the reactant. So here, what did I do to make my life simple? I doubled the concentration of the reactant. So when the concentration of A was 1, the rate of the reaction was 1 molar per second. So A was 1 molar, rate of the reaction, 1 molar per second. Then I doubled A, used twice the amount. Look at how that influenced the rate of the reaction. It didn't. So just by looking at this table, I can conclude A is not doing much to influence the rate of the reaction. So A is 0 order. Okay? Because when I doubled A, nothing changed. Right? You also want to know the units of the rate. So for this part here, I'm going to have to add a little bit. I'm going to add a page to show you the unit. Okay, we said for 0 order, the rate law is as follows. Rate equal K, open parentheses. Oh, A is the generic formula, right? Power 0. So this A power 0 equal 1. Therefore, rate equal K times 1, right? Rate equal K. The unit for rate is usually M because it's changing concentration over second. Therefore, this is K. So in this section here, you need to know units of K. So I told you, know this, the rate law, the two different forms. Know the implication, this part here, that changing one doesn't change, changing the concentration doesn't change the rate, and then know units of K. Okay? Oh, there's one more thing you need to know, the graph. Well, I think that's coming up later on. Yeah, that's coming up later on. We're still trying to understand the implications of this. Let me not get ahead of myself. Okay, we've seen first order. What does first order mean? In the first order reaction here, as we saw, again, starting with the general reaction, rate equal, this is a general rate law, rate equal K, A raised to the power N. If a reaction is first order, the rate is directionally proportional to the reactant concentration. So what they're saying here is, if you judge a chemical as responding this way, what does that mean? This is the implication, the meaning, and how it plays out in the lab. That means the rate of the reaction is directly proportional to the reactant concentration. Okay? So they show you here. What does that mean still? That means if you double A, the reactant, that will actually double the rate of the reaction. So if you want to double the rate of the reaction in the first order, just double the reactant concentration and that will happen. Okay? So let me show you this mathematically, how this plays out. Rate equal K. A is your generic reactant. We have no idea what it is. You can put A here. Since they put A, I'm going to stick with A to the power N. Since this is first order, N is equal to 1. So rate is equal to K, A, that's it. And this is the generic form of first order reaction, the generic form. So make sure you know that. Okay. What's next? Implication. Implication. What does this mean? How does this affect your life? Implication. Doubling A concentration doubles rate of reaction. Remember the other one, the implication, you did whatever to A and nothing happened to the rate. The rate remained the same, right? So here you can see in the little table, we have the implication. This is the one that's responding. You are changing A and then the rate is responding. So here, if we double the reactant concentration, the rate also doubles, right? I didn't work this out mathematically for the first one, but I'm going to do this for the second one. As far as our math is concerned, I'm going to look at just the relationship between rate and A, right? Rate and A. With rate and A, since they have this relationship, for here, I'll say to keep, for those of you who want everything step by step, I'm going to add one more step here. I'm trying to figure out how does A influence rate. I need to get K out of the way because I feel like K is in the way. So I'll make K equal 1. I don't know what K is, but I'm going to make it a number I can easily work with, right? I'll make K equal 1 and then start to deal with this. So that way it looks like rate equal A, like that. This is the first order. Okay, to figure out how this influences the rate, I have to have two experimental states, right? In the first experiment, experiment 1, I'll make A concentration equal to 1 molar. And then for experiment 2, I will just double A, make A concentration equal 2 molar, and see how changing the concentration of A is influencing the rate. We can predict, is it going to be fast, is it going to be slower? It's not zero order, so it's going to change it. The question is how. Okay, if rate equal 1 molar, sorry, if A equal 1 molar, then rate, since rate is equal to A, guess what? Rate is equal to 1 molar also. Because we said right here, rate is equal to A. If I now double A is now 2 molar, then rate is going to be equal to whatever A is. Rate is going to be 2 molar. See? So doubling A, going from this to this, just doubles the rate because they have a direct relationship, right? That's what they said, it was directly proportional. It's like a direct influence, proportional. The chemical directly influences the rate, okay? So back to the race thing, it would be like that runner that determines the race, yeah? If we're gonna win or lose, it's on this runner right here, depending on the level of influence. This is the direct relationship. Okay, but some runners have exponential influences. I saw this one girl on YouTube recently, and I was like, I wish I was a runner like her. I was more like the zero order. Okay, I wasn't bad. I just wasn't good. But sometimes not tanking the race is better than being negative, right? Yeah, they are negative orders. I've seen some reactions right there that slow the reaction. That wasn't me. I just wasn't that fast either. Okay, I gotta tell the truth. So anyway, so now let's look at the second order, right? Let me make sure I've covered all the things that we need to know right here. Oh, I've forgotten the units. We have to know the units. So you see right here the relationship, right? So finally, the units. Unit of K. Unit of K. So we know that rate in this first order is equal to K times the concentration of A. Okay. Rate usually has a unit of m over second. We're trying to solve for K. What is K? Since A is a concentration, it has a unit of m. We're trying to solve for K, so divide by m, divide by m. So what we end up having here is K is equal to m over s. You know the multiplying to divide rule, times 1 over m. So this and this cancels out, and we end up with 1 over s being the unit for K. So in first order reactions, K is 1 over second unit. Or K has this unit. K's unit is, okay, 1 over second. It's sometimes called 1 over second or per second, like this. This is the unit for K in the first order reaction. So later on you will see, because in class students usually ask me a lot of questions. They'll be like, wait a minute, does it mean that we can use the unit? If each of the orders has their own unit of K, can we work backwards and use the unit of K to figure out what order the reaction is? Because by this point, I usually have questions from students saying, well, if we're working problems, how do we know what order the question is? Do they tell us? Sometimes they do. Sometimes they don't. And then they were like, well, how do you know which one it is? And I'm like, man, they interrogate you. And I'm like, well, you can use the unit of K to tell what order the reaction is. Or they will tell you sometimes. Okay, so sometimes they will tell you, sometimes you can use the units of K. So this is K for the first order. When we get to the other part that we're discussing tomorrow, you see how the K unit is the same. So finally, second order reaction. I think that's right here. In the second order reaction, we start the same way with the generic form, right? And then this is the one that we saw first with the question I did last week. So we're kind of reviewing what we saw last week, right? Only last week we're doing the math first. Now we're learning the heart behind it or the message behind it. If a reaction is second order, the rate is directly proportional to the square of the reactant concentration. That's what we got. That's why doubling A will quadruple the rate of the reaction. Okay, this is what the rate law looks like, and this is a unit for the constant, and this is the implication. So let me go over that real quick, and then we'll start working problems. Yeah, we went over this where we said for a second order reaction, the rate law is equal to this, the generic form, A raised to the power n, where n is equal to 2. Okay, so rate is equal to K, A raised to the power 2. So how are rate and the concentration of A related? The concentration of A is squared to influence the rate. So if that's the case, then doubling A, like we said before, quadruples rate, because whatever number you have in here has to be squared, and then that influence is then exerted on the rate. Unlike the first order where whatever you do to A directly influences the rate. This is a direct relationship. Here you have an exponential. Exponential is intense. During the time of Corona, we understand exponential. If it was something that was removed, it's become very real to our heart. Exponential is above and beyond just direct, right? So here they're using the word direct, but it's a squared effect. They're using the term direct, but it's not really a direct relationship. It's the square of the effect. So what they mean by that is, once again, the implication, the meaning, implication. Because they use certain terms sometimes. If you're not very familiar with those terms, they can be, what's it called, confusing, but then you have to work problems. So if I'm going over this a lot, because you have to work problems where you have to understand this terminology, right? That's how I decided what was important as a student. If I saw a question on it, it was important, and I went back and relearned it. Okay, implication of these words. The implication here is we're trying to understand how rate relates to A squared. So to get rid of K, I'll just make K equal 1. That's kind of how you get rid of the influence of numbers, right? I don't know what K is. So to kind of get it out of the equation, so to say, literally, I'll make K equal to 1. So I'm trying to see how does A influence rate? Okay, I'll start with, what if A was just 1? Okay, if A was 1, then rate will be equal to 1 squared. Rate will be equal to 1. Okay? So if I doubled A, how would that influence rate? This time I've doubled A. Rate will be equal to 2 squared. Not just 2, but 2 squared. So rate will be equal to 4. So even though I'm just doubling A, rate is not also doubling. It will also double if this was first order. But since it's second order, whatever change you make in A, you get squared, the squared change in rate. So the rate actually quadruples. It doesn't double, quadruples. Because the relationship here is exponential, not direct, right? They say direct, but they say direct square. So you kind of have to read everything. It's directly proportional to the square. So this square is exponential relationship, right? Okay, now that we know the implication, doubling A doesn't double the rate, it quadruples it. It's like it doubles it twice. And in the end, what we see is quadrupling, okay? If you triple this, it will make it times 9, which I don't know what that word is in the quadruple version, but yeah. Okay. What was next? Oh yeah, the units. Now that we have this, we have to figure out the unit of K. Unit of K. So rate for second order equal K, A raised to the power 2. Let me add some more here. Not all the questions will be about the implications, but some questions will, so that's why I'm going over this. Rate has a unit of m over s, so that part is done, equal K. We're trying to solve for K. The unit for concentration by default is m, but now we're squaring it, right? So m squared. We're trying to solve for K. Divide by m squared, and then divide this part by m squared. So it's like m squared divided by this. Okay? Cancel, cancel. Now, I'm going to replace the divide with multiply. So I'm just going to put m over s times 1 over m squared equal K. I'm trying to solve for K. Remember, m squared is the same thing as m times m. M&M. Thinking of my favorite candy, peanut version. Okay. So we're trying to solve for K. Cancel m out, and we're left with 1 over ms, which is equal to K. So K is written like this for second order, or is written as K is equal to m power negative 1, s power negative 1, if you don't want to leave the units on the bottom denominator, right? Some people just prefer it like that. And so we have this. At some point, we'll see a summary table, and let me just kind of skip to that real quick. We'll come up to the math real quick. There's a summary table here. Let me see. I can scroll. And they go over all those units, and oh, there it is. We'll look at it again. But see, they had them in order of, no pun intended, they have them organized by order. 0 order, first order, second order. They give the generic rate law, rate law, rate law. The units, come on. This is supposed to be multiplied. So it's supposed to be m s power negative 1, s power negative 1. This is the same thing as m over s. And this is supposed to be multiplied here. This is 1 over ms, or m negative 1, s negative 1. So what we cover today is the first 3 columns here. We cover the orders, the rate law, the units. So later on in the chapter, when we get to this slide, we'll cover integrated rate law. This is when you bring in some calculus in here. No, calculus is not a prerequisite for this class, so you will not be asked to derive this. I'll just show you how we go from the first to the second. We'll talk about the graph and then half-life expression. So we'll fill in the gaps and complete the rest of this when we meet tomorrow. So now that we've seen how all of this comes together, now we're going to be looking at questions, right? So I have some questions here. We're going to be judging these questions based on what we just saw. Example, the rate equation for the reaction of NO and ozone is, okay, so given the rate equation, the rate law, equal K NO O3. K. You see from this right here, the order is first for NO and first for O3, right? So I'm just saying right here, okay? So you could say the overall order is 2, 1 plus 1, 2. They didn't ask you all that. I'm just saying since we're here. So if the rate is, so we're given rate is equal to 6.6 times 10 power negative 5 molar per second. So I'm right here. When NO concentration is 1.00 times 10 power negative 6 m, and then O3 ozone concentration is 3.00 times 10 power negative 6 m. Calculate the rate constant. Oh, solve for K. What is K? Oh, okay, we're trying to solve for K. So this is like you've gotten your rate law from the first order reaction thing. They give you the experiment numbers, that, and that. They tell you solve for K. We can do that, right? Just rearrange. I'm going to work this out on this side without adding pages. Rate equal K NO O3. We're trying to solve for K. Divide by NO O3 divided by NOO3, cancel, 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 cancel. Okay, so this is what K is. I'm going to flip this so that K is the subject, right? K is equal to, so now I have rate over NO. I'm just flipping it, that's all I did. So I can, the numbers I'm putting in should be on the right, O3. So now K is equal to, rate is the top number, 6.6 times 10 power negative 5. I have to keep checking because to make sure I transcribe this well, I got transcribing issues. 6.65 times 10 power negative 5 divided by NO concentration is 1.00 times 10 power negative 6 M, right? So I just got this bottom number here. 1.00 times 10 power negative 6, okay? 3.00 times 10 power negative 6 M. Somehow my brain just is like, when I'm copying things, my brain is like, vacation. I'm like, no, it's not. I'm still working on the problem, brain. Stay alert. I have a mind that gets bored very easily, so I have to keep myself engaged on purpose. 6.6 exponential negative 5, close parentheses. So I put the parentheses in here for y'all to see that I'm putting my parentheses to get my answer right. Take the top number, divide by both bottom numbers, open parentheses, 1 exponent negative 6. Parentheses are very important in this pursuit. Divide by, open parentheses, 3 exponent negative 6 to the right, close parentheses. Okay, I get K as a huge number. It's 2.2. Ooh, it's a bunch of zeros. Hold on. 1, 2, 3, 4, 5, 6, 7. 2.2 times 10 power 7. Okay. Now I gotta think about the units though. Okay. I had 2 M's in the bottom. It cancels out one of the M's at the top. So I end up with an M on the bottom and an S on the bottom. Oh, this is consistent with second order, right? Yeah, and the overall one is second order, so the K is a second order one. Okay. So this is K. This is our answer. See how it all ties in together? The unit here is consistent with the second order K that we just figured out recently. So the K goes with that. Now the individual ones are first order, but the overall is second order, right? Okay. Oh yeah, I forgot they worked it out here. Right. Okay, this next one. A reaction has the following rate law. Rate equal K acetaldehyde. I'll just write acet, okay? Acet will be the representation of acetaldehyde. It's a long word to write. I should write ACE. That's not important. Acet, okay, for acetaldehyde. Okay, obviously the overall order for this is 2, second order, right? What is the rate of the reaction when the acetaldehyde concentration is 1.7 times 10 power negative 3? Okay, so they want us to solve for a rate. What is the rate? If the acetaldehyde concentration is 1.75 times 10 power negative 3 molar, okay, and then the rate constant is, and then K is 6.73 times 10 power negative 6 per molar per second. That's consistent with second order. You see how it's all kind of coming together? You want to pay attention to the K to make sure you're understanding, you know, they didn't say second order, but this is obviously second order based on that. And then the K, that second order K goes with that. Let's see. Okay. I think I'm getting too excited. I'm sorry, I have to be excited. There's not a whole lot to be excited about these days. Okay. Rate equal, what is K? 6.73 times 10 power negative 6, right? 1 over ms, that's the unit for K, times acetaldehyde, the unit here is 1.75 times 10 power negative 3. I gotta square this. So I'll deal with the square number first so I don't forget. Open parentheses, 1.75, exponent negative 3 to the right, close parentheses, and then square this. Square. Okay, I got some numbers, a really small number. So what I'm going to do here is, I'll just rewrite it. 6.73 times 10 power negative 6, 1 over ms, times this number here. Wow, I get a 3.063 times 10 power, hold on, 1, 2, 3, 4, 5, 6, power negative 6, m squared. So I take the second number, multiply by, open parentheses, 6.73, exponent negative 6 to the right, close parentheses. And I end up with 2.06 times 10 power negative 11 for my rate, okay? What are my units? I have m squared, that means it's m times m. So this is essentially m times m, right? One of the m's cancels out with the bottom m, and I'm left with, oh, one m still on the top. The bottom m is gonna be, oh, the bottom m is gone, right? So I'm just left with m over s, which is consistent. The unit for rate is m over s. Let me tell y'all, okay, my past. I was so confused about what I was doing. I was still not really very familiar with order of reaction rate at some point. Now I've learned it, right? But then I was trying to figure everything out. I wasn't sure about K. I just wasn't sure about a lot of things. So I used the units to anchor. I knew m over s was rate. So if I worked out a problem and they said rate and I canceled out the unit and it ended up as m over s, then I knew I got the rate. If I got the order of reaction, there were no units, I knew I got the order. If I was trying to solve for the different Ks and I got the right unit, I knew I was in the right track. So I went from hating dimensional analysis to using it as an anchor to tell me I was doing the right thing, right? Because I needed that affirmation constantly. And the teacher didn't have time to affirm me every time I was doing stuff. She wasn't there to say, you're doing so great. But the units was telling me, you're doing so great. Anyway, that's how I took it, right? If I got the desired unit, I had to be doing something right. Anyway, that's how I saw it. So, yeah, right there. So they get that. So, yeah, as we look at all of this, we see the summary of the reaction rate. I added the summary here to kind of remind us of what we've seen so far and what you want to make sure that you have covered. We had talked about the average rate of the reaction, right? Plus the terminology. We have average rate. With the average rate of the reaction, this is where stoichiometry comes into play. So I talked about this last week. The average rate of the reaction, they can ask you to figure out the average rate. So for the most part, they use the terminology average rate. You will have some kind of balanced equation. So let me go ahead and expand on this a little bit, because I would rather get into integrated rate laws tomorrow versus start today. Okay, let me think of a balanced equation. Make one up between hydrogen and oxygen, a very popular one to make water. Okay, so we got hydrogen, oxygen combined to form water, and then yeah. So if they're asking you to find the average rate of this reaction, they can ask you to find the average rate. And even if, don't get so hung up on the words, even if they don't ask you include the word average, because sometimes they don't, and the authors make me angry sometimes, like I usually have some choice thoughts for them or against them. Look at everything else they give you. They can ask you to find the average rate or to write the average rate according to reactants or products. So if they ask you to write the rate according to the reactant and product, and they didn't say rate law, then we are back to the beginning of the chapter where you would say the rate of the reaction. Remember, this is a general formula, right? Was going to be 1 over the coefficient from the balanced equation. Oh, I'm not going to the door. My husband has to wake up or get up and answer the door. Okay, 1 over the coefficient. And if you had a reactant, don't forget to put a negative, right? Negative 1 over the coefficient. and then you have the change in the concentration of the reactant formula over the change in time, okay? And this is the way you will use to get the rate of the reaction if they tell you to find it according to the reactant or the product. You will use this method. So I'll give you an example. I will use hydrogen here. You say rate equal, I'm writing this the equation. I don't have the actual numbers with me. Negative. What's the coefficient on hydrogen? 1/2, and then changing reactant. Change in concentration of H2 over change in time. So what is the other way you can tell what kind of question they're asking you? They will give you, in this case, 2 hydrogen concentrations, right? They'll tell you the hydrogen amount in the beginning, so say at time 0, and they'll tell you the hydrogen amount after a certain time. So let's say in the beginning you had 1.00 molar. After a certain time you had 0.500 molar. You will have those numbers. Then they'll tell you the beginning time. Say the beginning time was 0 seconds. Usually the beginning time is the beginning, so that's 0 seconds. And then the final time, let's say 10 seconds. Let's keep this easy. I'm just making up these numbers. So if you have the beginning amount of hydrogen, which was very high, then you have half of it ran out, and the time that passes 10 seconds. What is the rate of this reaction by figuring out the rate by monitoring hydrogen? Well, I have the formula here. 1/2 change in hydrogen concentration. Use the second number, the final amount, minus the initial amount. And then over change in time. Final time, 10 seconds. Oh, I didn't put my units here. 10 seconds minus initial, 0 seconds. Okay. Now, I mentioned this before last week. Rate is always positive. So if you look at this, 0.500, I'm doing the parentheses first, minus 1, I get negative 0.5. Then divide by the bottom one, divide by 10. I end up with, in the parentheses, negative 0.05 m over s. Yeah, I'm trying to wrap this up, times negative 1/2, right? So when I work everything out, I end up with divide by 2. I end up with 0.025 m over s. Okay, this becomes my rate based on the little calculation I did. So when they ask you to figure out average rate, you can figure out the same number by using this generic formula, which I wrote better over here. If you're following the reactant, you can also figure out the rate by looking at the product. But if you're trying to look at the product, your formula has to be different right here. Okay. So if you're trying to solve for the same thing, looking at the product, let me just kind of wrap that up real quick. So average rate from product, your equation will be very similar, but it will be rate equal to 1 over coefficient. This time you will not put negative here, you leave it as positive, and then times change in product concentration over change in time. Okay, this would be positive. That's the difference. And they have to give you the 2 numbers again for the product, the 2 numbers for time. You work it out, you get rate. Your answer should be unit m over s, right? So we just kind of summarize this part here. Summarize, done. With the rate law, remember rate law, if they ask you to find the rate law always has this formula, rate law. Rate equal K, and then you may have 2 reactants, maybe you may have 1, I don't know, raised to the power m, the second reactant raised to the power n. And then remember from here, you have m is the order, n and m orders of reaction. And then we said overall order, m plus n. Okay. Where did that box come from? Maybe it's something I did earlier. Okay. Overall order, m plus n. Oh, okay. Yeah. And if they ask you to solve for k, if you're asked to solve for the magnitude, which is the value of k, remember, k is just equal to rate divided by the reactant concentration raised to the power m, and then the second reactant concentration raised to the power n. Yep. And that's a summary so far of what I covered. So when we meet next time, which is tomorrow, and I'll send you guys a reminder. I have to send myself a reminder, then send you guys a reminder, but you know how that works. I'll say start here. Okay, so we'll start right here. So we'll start with integrated rate law so you can see how this comes up and how we talk about the reaction at different points in time. Okay, this is all I have for today, and then we'll finish, hopefully we'll finish this chapter tomorrow. Does anybody have any questions about this? I see it's just one person left. Do you have any questions about this? Okay, so we'll bring in the graphs tomorrow as we try to summarize this topic and then complete the topic to the end. I mean, I'm hoping we get to the end, but yeah, that's the goal. Okay. Okay, I will see you tomorrow. Have a nice afternoon. Okay. Thank you.